Now in today's lecture, we will continue ahead in kinematics with our first instance of two-dimensional motion. But now, I mean, in general, we will talk about kinematics in 2 and 3 dimensions from this point onwards. And we will start with the next part, that is the part which is two-dimensional kinematics with projectile motion. Okay. Next session that I will keep some time aside for questions and doubts. And in that, I will include some time for questions and doubts from the worksheet that I had given you for one-dimensional motion earlier. And also, if at that stage any questions are pending from your major test question bank, but I think that has anyway been discussed with you, so not be a problem. So let's start today's session.
Sir, can you resend that worksheet because my badge just got changed? It was shifted from greenhouse to blue.
Okay, I will resend the worksheet on the blue house batch that you have got now. Okay.
Sir, can you please tell me what was the last time in the class? Blue house.
Same thing in all batches. Like we've completed one-dimensional kinematics before the test.
Okay.
That's the last thing that has been done.
Okay.
So we're starting with the next section, which is beyond one-dimensional kinematics. So today we will start with the next topic within kinematics, which is projectile motion. So in a sense, we have already seen one case of projectile motion, which is the vertical projectile motion. But when we talk about projectile motion in general, we mean the more general case where there is oblique projection. So oblique projection means that the object is projected at an angle to the vertical or at an angle to the horizontal, such that it has got both a horizontal and a vertical component of motion. So before this, let's quickly understand that this is an example of kinematics in 2 dimensions. So when we talk about kinematics in 2 or 3 dimensions, then the difference is that there is the vector notation. Or the kinematics parameters. So the position is given by a vector quantity, which we generally denote by R, which becomes xi cap plus yj cap plus zk cap in 3D. Okay. Where x comma y comma z, the coordinates of a particle at some time t, suppose, then R represents the position vector. It's called the instantaneous position because it's at that time t. Then displacement s, it just becomes the difference in position vector. S is the displacement from t equal to t1 when the position was r1 to t equal to t2 when the position is r2. And accordingly, the velocity vector becomes rate of change of displacement with respect to time, or that's the same thing as rate of change of position with respect to time. And finally, the last parameter, the acceleration vector, becomes rate of change of velocity with respect to time. So we will see how these things are applied in the coming sections, including projectile motion. But the only thing we need to be mindful is that now we are switching from 1D kinematics to 2 or 3D kinematics. So our notation for the parameters changes from scalar notation that we used to use in 1D. Like position was given by a single coordinate x, displacement was given by delta x, velocity was given by dx by dt, and acceleration as dv by dt. Now they become vector quantities, which are generally expressed in the unit vector notation. I cap, j cap if it's 2-dimensional, and I, j, and k if it is 3-dimensional. So there's nothing more to this. You just need to keep in mind that the parameters, these 4 important parameters, are now vector quantities. We're using the vector notation. You'll see its application immediately in projectile motion. Okay. Now, moving on to the actual topic for today, projectile motion.
Sir, just a second, can you go?
Okay.
Yes, sir. Done.
Okay. So projectile motion is this situation where, like, from the ground level, or you can say from some horizontal plane, what we are doing is we are projecting an object, but we are projecting it with an initial velocity. Projecting just means throwing it. A projection is another word for ordinarily what we mean by throwing. So we are throwing or projecting an object like a particle at a velocity which is neither vertical nor horizontal, but is at some kind of angle with respect to the horizontal. So an object, a particle, is projected with what is called an oblique velocity u, okay, from a horizontal surface. So once the object leaves contact with whatever projects it, like if you projected it leaves contact with your hand, okay, what is happening is it goes in this kind of a path, because like it was here at t equal to 0 when you threw it. After some time when it reaches here, the only force that is acting on it is gravitational force, which is vertically downwards. So that is what is pulling it down, and hence its velocity will be changing in this manner. At some time t, its velocity will become like this. After some time, it would have reached the highest point. It will start descending after that. So that is the effect of gravity. Yes, exactly. But Jitesh, the only difference is in badminton, the shuttlecock is like a very comparatively an object made with feathers and a cock. So it is designed in such a way that it is influenced by air resistance also a lot.
Yes, sir.
But if you compare that with something like a hockey ball or a cricket ball, it is not so much influenced by air resistance. It is only influenced by gravitational force. So the type of projectile motion that we are studying here, it is going to be under the action of gravity alone. That means the type of object we are talking about, it should be such that it's influenced only by gravity primarily, and other forces like wind resistance, air drag, etc. are negligible. So for that, we need high density objects like a stone or a heavy, hockey ball. Even a football is, not that much in density because it's filled with air inside. No? So especially if you give it spin, then because of something called Magnus effect, the spin creates difference in pressure around two. Yes, javelin throwing is also an example, okay, of projectile motion. So basically, anything which is thrown in the air is an example of projectile motion. But here we are studying the most simple type of projectile motion, where the nature of the object that we are throwing is such that we can ignore any other force apart from gravity.
So
Like,
only here we are taking the gravity, not the air
yes,
resistance, which is okay.
yes, yes. Air resistance should be negligible in this case. Okay.
Yes, sir.
So practically that will work out to a situation where the object is made of a high density material, like a heavy stone or like a hockey ball or something like that, as I told you. Whereas even when you throw a table tennis ball, for example, it's hollow inside, so its density is less. So it is influenced quite a bit by air resistance compared to the weight. Okay. Assuming only gravitational force, mg acting on it while it is in air drag or wind resistance type forces, are assumed to be negligible. In this particular study of projectile motion. Okay, so now in this, u is called the projection velocity. Whatever velocity with which we throw it at t equal to 0 from the ground level, that is called the projection velocity. And naturally, its magnitude is called the projection speed. And theta is called the projection angle. It is the angle of the projection velocity with respect to the horizontal. When we talk about projection angle, we always take the angle with reference to the horizontal axis, not with reference to the vertical axis. 90 minus theta will become the angle with respect to the vertical. So if a question directly tells you without giving you a diagram that the projection angle is 30 degrees, you should remember that it's the angle with respect to the horizontal and not the angle with respect to the vertical.
So,
Yes, yes, Bhutan.
so what if the air drag and wind resistance is taken into the consideration then?
Then the motion will be described by equations which are a little bit more complicated compared to what we are learning over here. That's the difference. Okay.
Okay, sir.
This is like a simple model of projectile motion. And if some other forces like air drag and all that is taken into account, then it becomes a slightly more complicated version of projectile motion. So the equations that we'll have to generate then will become more complex.
Okay, sir.
Okay, so now some more terms related to projectile motion. So one term that you will commonly see is called the horizontal range of a projectile. So for example, we've all been talking about the range of the throw that was made in the Olympics to win the gold medal. Not mistaken, it was some 115 meters, something like that. So if the projectile starts from the ground at t equal to 0 and then comes back and hits the ground, okay, okay, at some time, let's say capital T, then the horizontal distance between the point of projection and the point where it hits the ground, that is called the horizontal range. So first of all, capital T here is called the time of flight. That is the time taken from projection, that is T equal to 0, till the projectile. The projectile is the object that has been projected, returns to the horizontal surface, or you can say the horizontal plane of projection. And R is called the horizontal range. That is simply the distance from point of projection to point of impact. So we'll see that these are standard quantities for which we will develop formulae, just like we had formula for maximum height and time of flight in vertical motion. Now we have one more term here, which is the maximum height the projectile achieves from the ground level. So for that also we'll develop a formula. So ultimately what we'll see is all these three parameters, that is capital T, the range R, and the maximum height H. They depend on both the things, the speed of projection U and the angle of projection theta. So all these three quantities T, R, and H will be expressed in terms of U and theta.
Sir,
Yes.
can we say that the range R is similar to the distances?
The range is actually the distance between the point at which you've thrown the object till the point at which it comes back to the horizontal plane from which you've thrown. Distance is actually, if you talk about distance traveled, that is going to be more than the range. Range is more like the displacement. You're getting it, no? Because it's
Yes,
the
sir. Yes,
straight
sir.
line. Whereas the distance would be actually this curved path, which is not so much of importance here. What is of importance for us is where it's landing on the horizontal plane. So that straight line path from where it started to where it landed. So it's actually the displacement from initial to final time.
Okay, sir. Got it.
It's like the magnitude of that displacement.
So even the distance covered by the body in flight can be calculated. Like,
It can be calculated, but generally that is not something of importance.
Okay, sir. So, but it requires just from U and theta only we can have a formula.
Yes, yes. For any motion, there is a way to calculate the distance traveled. That comes by integrating the speed with respect to time.
Okay, sir.
Just like displacement comes by integrating velocity with respect to time. Like that, we can calculate the distance traveled by integrating speed with respect to time.
Okay, sir.
Okay, so now having understood these three basic parameters, now we come to the mathematical analysis of projectile motion. Okay. So basically, we want to develop the equations of motion. For a projectile. And then using that, we will develop the formulae for those three things, the range, the maximum height, and the time of flight. Okay. So when we start any kinematics problem to basically define the equations of motion, we must define a reference frame. Without that, we cannot even define position. We must have an origin, we must have a system of coordinates. So here, the reference frame that we select is very simple. We take the point from which we have projected the particle as the origin of our system. We take the vertical as our y-axis. Logically makes sense. Okay. and we take the horizontal as our x-axis. So from the ground level, wherever we have projected, that point is taken as the origin. The x-axis is the horizontal axis, and the y-axis becomes the vertical axis. And the other thing is we start our clock, that is t equal to 0 for us is at the time of projection. So the reference frame says that the origin is at the point of projection, and x-axis is the horizontal axis, and y-axis is the vertical axis. Okay. And the initial velocity vector u is in the xy plane. Okay. So the motion itself will be in this two-dimensional xy plane. It will be restricted to this two-dimensional plane because the initial velocity is in my xy plane, and the net force that is acting on the body, gravitational force, that is along the y-axis, the negative y-axis. So there's nothing to give it any z component of motion. So the motion is restricted to this two-dimensional plane. So once we have defined this, now we need to define our parameters in component form. Okay, so therefore, the initial velocity vector u will be expressed as u cos theta I cap plus u sin theta j cap. Or we can say that the initial velocity has components, x component this much and y component this much. Okay. And acceleration is equal to minus g j cap. Okay. So it is a, or we can say that the x component of acceleration is 0 and the y component of acceleration is minus g. So it is a case of uniform acceleration. So from this we can understand how to write an equation that if we have projected at some time t equal to 0 with u at an angle theta, then at time t what is happening to the particle, where it is reaching in terms of xy coordinates, okay, and how much the velocity has become. These two things we can calculate using these parameters, using this and this. Okay, so from this point onwards, to understand the motion better, what we do is we divide the motion divided it into two components. The horizontal component or x-axis and the vertical component, that is the motion along the y-axis. So as you can see from here, the initial velocity along the horizontal axis is u cos theta, and the acceleration along the horizontal axis is 0. So that means along the horizontal axis, there is uniform motion, that is 0 acceleration. Okay. So at any time t, the instantaneous x component of velocity will remain u cos theta. Okay. And the x component of displacement will therefore become velocity into time. When there is no acceleration, the displacement becomes velocity multiplied by time. Whereas along the vertical axis, we can see what is happening. The initial velocity is u sine theta, okay, but the acceleration is minus g. So it's that case of uniformly accelerated motion. So our three equations of motion will apply that at some time t, the velocity will become like this. Okay. So velocity at any time t will become u sine theta minus gt. Displacement will become u sine theta t minus half gt square. And we can also write the third equation of motion, that sorry, okay. Whereas here these equations are simply coming from the fact that it's coming from this. So having divided the motion into the two components, the horizontal component and the vertical component, so you can see that the horizontal component of motion is described by these two equations, and the vertical component of motion is described by these equations. This is the vertical velocity as a function of time. This is the vertical displacement as a function of time, and similarly this and this are horizontal.
Can you scroll up?
Scroll up, is it?
Not that one.
This what?
Yeah. Yes, I'm done. Can you scroll?
Oh. So these are the most important equations of motion, the ones that I have put in the boxes, okay? Particularly the tick mark ones, the 4 tick mark ones. We'll see how we use these 4 equations only to determine the formulae for all these quantities like range, maximum height, etc. And for any other calculation which is related to projectile motion. Okay, so now let us see how we put these equations into work.
One minute.
Yeah.
Yes, sir.
Oh. So coming back to a visual representation of the projectile motion. So my horizontal axis, my vertical axis, okay, and the point of projection being the origin. So if I project it with the initial velocity u at an angle theta at t equal to 0, and the projectile goes off in a path like this, and then eventually it comes back and hits the ground, which is in this case my x-axis at some time t. So in between at some time t equal to t, if it is here, its velocity is v, its coordinates are x comma y. Okay. And then we can see that from this time to this time, 0 to t, the displacement will be this vector here. Displacement is the shortest line or
Yes.
the vector joining the initial position with the final position. Okay. So in this interval of time from 0 to t, we can see that at t equal to t, the displacement will be nothing but x I cap plus y j cap. So the formula that we have for that is like this now. X, remember, was u cos theta into t because it's moving with a uniform velocity along the x-axis. But the y component of displacement is u sine theta t minus half gt square because it has a uniform acceleration of minus g along the y-axis. Okay. So this becomes the vector notation for that x and y thing, the position or the displacement. And similarly, the velocity is having some x component and some y component. And the formula for that x and y component we've seen above. Okay. The x component remains constant, so it is u cos theta. But the y component has an acceleration of minus g. So it is u sine theta minus gt. So these two equations are the same as the above four equations actually. But because they are vector equations with two components, so now you're writing those equations in the form of two vector equations instead of four scalar equations. X as a function of time, y as a function of time, vx as a function of time, and vy as a function of time. Now we are just writing it as two vectors. Okay. Now the next thing that is going to be important here is that at the time when the projectile comes and hits the ground, that is what we call the total time. So at that point of time, you can see that what is happening is that wherever the particle is landing, its y coordinate is becoming 0 and its x coordinate is becoming the range. Okay, so at t equal to capital T, the x coordinate becomes the range and the y coordinate becomes 0. Okay. Whereas we'll also see that when it reaches the maximum height, logically at that point of time, what should happen? The velocity should become horizontal at that instant. Okay. So at the point of maximum height, the y coordinate should become h and the y component of velocity should become 0. So the velocity should just become u cos theta I cap. So using these two hints, you can say, okay, or using these two sort of guidelines that what is happening at capital T and what is happening at the maximum height position, we will develop the formula for maximum height and total time of flight and range. Okay, so you'll see that going back to, I'll just write down over here these equations. X as a function of time was u cos theta t. Y as a function of time was u sine theta t minus half gt square. And the x component of velocity was always u cos theta, whereas the y component of velocity was u sine theta minus gt. So we can say these are our primary equations 1, 2, 3, and 4. So now we will see that this thing, that the range and the time of flight. So from equation 2, we will see that at t equal to capital T, what should happen? The y coordinate should become 0. So u sine theta capital T minus half gt squared should be equal to 0. So we factorize this, we've got this. So that gives us two possible solutions. T equal to 0, which we won't take because that's the initial time. And the second root of this equation is that it is u sine theta divided by half g, or 2u sine theta divided by g. So this becomes the formula that we get for this thing, time of flight. So as I told you, the time of flight, capital T, all these parameters are time of flight and h, they will depend on these two things. They depend on the speed of projection and the angle of projection. These two things they depend on. So here you can see how it depends on u and theta. Of course, g is also there, but g is a constant. Okay, g is a universal constant for all projectiles. So how a given projectile will develop a certain time of flight and a maximum height and all that, it depends on what speed we are projecting it with and what angle we are projecting it at. So this is that relationship. Okay. So just make a note of this thing first, then we'll also see the other two quantities, the range and the maximum height. They will again come by using these conditions that I've written over here in this note, using these conditions and the four equations over here. These same four equations are written in vector form over here and here. There's nothing different between these equations in vector form and these four equations here. The only difference is here they are written in component notation, here they are written in unit vector notation.
So in short, we are just finding the maxima of that equation, like for the T wala equation.
For h, na? Yes, we'll find the maxima of the second equation. Y is maxima we can find. Okay. And similarly for the range, we have to just find the value of the x coordinate when the time is capital T. So we already found the value of capital T, na? So we'll plug that in equation 1. So that will give us the formula for the range.
Oh.
Okay, so as I said, next thing, let's develop the formula. Okay.
Yes, sir.
Okay, so next up, let's look at the formula for range and maximum height. So again, we can see that from equation 1 that we have over there, at t equal to capital T, the value of x should be r. So we'll get that r is equal to u cos theta multiplied by capital T, and then plug in this value of capital T here. So we'll get u cos theta multiplied with 2u sin theta by g. So we get this 2u square sin theta cos theta divided by g. You can remember like this also, but we can use trigonometry to reduce one more step. I mean, simplify it one more step. 2 sin theta cos theta is sin 2 theta. So this becomes, as a formula, it becomes like this, that the horizontal range is u square into sin 2 theta divided by g. Okay. Now, the other thing we'll also use here is that at the point of maximum height, okay, velocity's y component should be 0. So therefore, from equation number 4, which was Vy as a function of time, Vy, which is u sin theta minus gt, should be 0 at the point of maximum height. Okay. So that means that time should become u sin theta divided by g, which by the way is capital T by 2. So there is one important fact, that this implies that the projectile reaches its maximum height at half the total time, which means that once again the ascent and descent are symmetrical. So this is also another important fact. And then we'll put this value of time in the second equation. So that will give us the formula for the maximum height.
And
So now we put this in equation 2 again. So y is equal to h at t equal to capital T by 2, which is u sine theta by g. So we have h is equal to u sine theta t minus half gt square. So that is t is again u sine theta by g. Yes, that Anandita will understand that in a moment. Okay, you can see that in the formula of range, the quantity sine 2 theta becomes the maximum when the angle of projection is 45 degrees, because 2 theta becomes 90 degrees. So at a given speed of projection, if you want to achieve the maximum range, the angle at which you should project should be 45 degrees. Any angle of less than 45 degrees will be less effective in giving you a range for that reason. Okay. So that is the maximum range condition. That's another thing we'll analyze very soon. Okay, so so this is the derivation of the three formulae, but you should understand the logic behind the derivation rather than memorize all the steps. So you can see that time of flight is 2u sine theta by g, or you can also remember it in component form as 2uy divided by g. This is also very effective because in vertical motion, you remember the time of flight was 2u by g. So here in projectile motion, that vertical velocity u is replaced with a vertical component uy or u sine theta. Then the horizontal range, which as a formula we write as u square sine 2 theta by g, but you can also remember it as the horizontal component of velocity into time. So that is u cos theta into 2u sine theta divided by g. So this is also a very effective way of keeping in mind this formula. Okay. And the maximum height u square sine square theta by 2g. So this also you can remember in such a way that it's relatable with the vertical motion concept that we had learned earlier. There the maximum height was u square by 2g. Here you just replace u with the vertical component uy or u sine theta.
So what's the alternate definition of T? Can you read it? Vy?
Sorry, come again. The alternate definition of
T, capital T, Vy, right? 2 Vy by
uy, 2uy by g, because uy is u sine theta. No?
Okay.
The initial velocity is vertical component is u sine theta.
Yeah.
Ux is u cos theta. So instead of theta, we can also define everything in terms of ux and uy. Okay. On the left hand side here, everything is defined in terms of theta and u. Here it is defined in terms of ux and uy. Okay, now next thing, we look at what we were just talking about a moment back, the maximum range condition. For a projectile launched at a given projection speed u, okay, the horizontal range will be maximum if theta is equal to 45 degrees, and that maximum range becomes u square by g. So this is easily understandable from that formula, u square sine 2 theta by g. So range's maximum value will be u square by g into sine 2 theta's maximum. And sine 2 theta's maxima, as you know, is 1. And the condition for that is that the angle 2 theta should be 90 degrees. So theta should be 45 degrees. So if we want to throw something most effectively as far as horizontal range is concerned, then we should be able to launch it at a 45-degree angle of projection. Then for that given speed of projection, we will get the maximum range. So that is called the maximum range condition. Okay, so let's look at our first example of a numerical problem. So a ball is projected from a horizontal plane at t equal to 0 at a speed of 50 meters per second and angle of projection 37 degrees with respect to horizontal. So first thing is very simple. We'll use the formula to find the range, the maximum height, and the time of flight. Second thing is we'll find the displacement and velocity at t equal to 2 seconds and t equal to 4 seconds. And then next thing what we'll do is we will find the displacement from t equal to 2 seconds to t equal to 4 seconds. Okay. And the average velocity. Okay, take g's value as 10 meters per second. So just try out this question. So the first part you can completely do by the formula. For the second part also you can do by the standard equations, the 4 standard equations in component form that we had written. X and y as functions of time and vx and vy as functions of time. Just using those equations you can solve. Just try this out, people.
Sir,
Yes.
do we have to give displacement and velocity in the second question in magnitude, like in vector form
No,
or in
you
the
have to give
magnitude?
it in component form in I cap and J cap notation.
Okay,
I use the standard thing that x axis is horizontal. Okay. Jinendra and Jitesh, your answers are correct. Jitesh, only check the time of flight. Okay.
Yes, sir.
Might have made us calculation error in that. Okay. I'll put up the answers in a minute. Okay. And you two can start with the second part also. You got the first part. Okay, Jitesh is correct now. Vedant, your answer to the second part is correct. Jinendra, yours is also correct. So the first part I'll just put up the answers here. Range should be 240 meters. Maximum height will come out to be 45 meters. And time of flight will come out to be 6 seconds. Yes, Siddharth, very good. That's correct. Okay. So for the second and third part, use these equations that Vx is going to be u cos theta. So that is 40. Okay. And Vy is u sin theta minus gt. So Vy as a function of time is 30 minus 10t. So this equation. Okay. And x is u cos theta t. So x as a function of time is 40t. And y is u sin theta t minus half gt square. So on substitution, the y coordinate as a function of time should be like this. So make use of these equations for working out the second part.
Sir,
Yes,
sir, what is written in the third part? Time is a time 2 seconds to
4 seconds. From 2 to 4 seconds. Okay. This part now?
Yes.
Yeah, that's the same interval, 2 to 4 seconds. Yeah, so this is 160. Okay, so in the third part, you'll see you'll require this only. Third part, the displacement from 2 to 4 seconds will be equal to the displacement at 4 seconds minus the displacement at 2 seconds. From this position to this position. And the average velocity from 2 to 4 seconds will be the displacement from 2 to 4 seconds divided by the time interval.
yes, sir. Done.
Right. So you'll also notice that there's a kind of symmetry to the answers in second part B and C. You can see the y coordinates are the same for both of them, and the y component of of velocity are also symmetrical. It's plus 10 and minus 10. So we will understand that next. That happens because again the projectile motion has a symmetry for the ascent and descent. Yes, very good, Siddharth, Jinendra. The answers are correct. Vedant. Yes.
So I'm the displacement
Yeah.
from 2 to 4, getting it only on the only I.
Yeah. No, because the y coordinates are the same. Na? So that means that if you were to visually draw the diagram, na, that at 2 and 4 seconds, they are at the same level. They are at the same height from the ground. So the displacement is only along the x-axis, right?
Yes, sir.
And that is why the average velocity will also be only the x component of the velocity.
Sir, if we subtract velocity at 4 seconds from means velocity in 2 seconds from velocity at 4 seconds, we get minus 20 J.
Minus 20 आ रहा है क्या? Just check. See, it is 30, Vy is 30 minus 10 t. Na?
It's minus 10. Minus.
So at t equal to 2, it will become 30 minus 20. Na? That's 10. And at t equal to 4, it will become 30 minus 40. Na? That's minus 10. So I think my calculation is correct, beta. Is it all right now?
Yes, sir.
Okay. Now see, what I was telling you about now, if you notice that this value and this value, they have a symmetry. Their y components are opposite of each other, plus 10 and minus 10. And these two also have a symmetry that their y coordinates are same. Now it is not just a, it's not a coincidence that is happening. It is actually because the projectile motion also has a symmetry. That is, the ascent and descent are symmetrical. So that's the point we'll explore next. Okay, the symmetry in the ascent, that is t equal to 0 to t by 2, the y coordinate goes from 0 to h. Okay, and the descent, so it comes down from t by 2 to 0. Y coordinate goes from h to 0 in projectile motion. So let's understand that symmetry visually first. and then we will see how it applied in this particular example. So the first aspect of symmetry, we've already seen that the time is divided exactly in half. It reaches the maximum height at t equal to t by 2. And when it reaches the maximum height, the velocity is only u cos theta. And now we'll see not only that, but also this x coordinate over here. So at t equal to t by 2, maximum height. Okay. But apart from that, you'll also see that x is half the range. Whereas at t equal to t, the x coordinate is equal to r and the y coordinate is 0. Now, in between, if you see some time at which it has reached somewhere here, suppose the time here is t1, the x coordinate is x1, and the y coordinate is some y1. Then we will see that it will again reach that same height on the way down at some other time t2. And that coordinate will be x2. But if these two times are such that if y equal to y1 at t equal to t1 and y equal to y1 again at t equal to t2, then it must imply that first of all t1 plus t2 is equal to capital T. Okay. And x1 plus x2 is equal to the range. Okay. And if v1 is equal to u cos theta plus some vy at t equal to t1, then v2 will be equal to u cos theta minus of that same component at t equal to t. So that is the symmetry, that these 2 points are symmetrical. So whatever this velocity v1 over here, this velocity v2 has that property that has the same magnitude as v1.
Only the j cap changes its sign.
Yes, changes its sign between that time t1 and t2. Okay. So that is what, so that's the example that we saw over here, that in this example where u was 50 meters per second and theta was 37 degrees, our time of flight came out to be 6 seconds. Okay, so therefore t by 2 was 3 seconds. Okay, so therefore if t1 was 2 seconds and t2 was 4 seconds, okay, we saw that because t1 plus t2 was equal to capital T, there was that symmetry. In this example, there was that symmetry. Okay. So V1 was 40 I cap plus 10 J cap. So you can see that V2 was 40 I cap minus 10 J cap. And the Y coordinate at T1 was, how much was it now? 40 meters. And the Y coordinate at T2 was also 40 meters. Because this was happening, because T1 plus T2 was equal to that for these values. So it's not surprising that we got that symmetry. Okay. So this symmetry is something important to keep a note of, okay, in projectile motion. Just like in vertical motion, we had seen that there is a symmetry such that the ascent and descent are actually along the same line, and it's like a mirror image. It exactly retraces its path. So here it's not like that. It's a two-dimensional motion. But again, you can see that this part of the motion is like a mirror image about this symmetry axis. This is like a symmetry axis. So this part and this part, they are like mirror images of each other. So at any two points which are on the same level, the velocities will have same magnitude and the y coordinates will be the same, and the time will also be symmetrical. If this time is t1, this time interval from here to here is t1, so from here to here should also be t1. So t1 should be the same as t minus t2. That is from ground till this point, whatever time it takes t1, then from this time t2 to ground, it should take the same amount of time. So t1 plus t2 is equal to capital T. Okay. So this is the symmetry in the projectile motion, the symmetry between the two parts of the motion, the ascent while it is going to the maximum height and the descent while it is descending back from the maximum height to ground.
Sir, in the descent, in the note 1, you wrote that t is equal to t by 2 to t is equal to 0. It should be t, right?
No, but ascent is from t by 2. Oh,
Descent.
yeah, correct. Yes, in the descent it is from t by 2 to capital T. That's correct. Yes, just make this correction here if you've already written this down during the descent.
Sir,
Yes, beta.
can you explain how you wrote x1 plus x2 is equal to r?
Yeah, that also I'll explain. See, it was happening here also, no? That what was the x coordinate at this time 2 seconds? Remember, it was 80 meters, right? And what was the x coordinate at 4 seconds? It was 160 meters. And you can see that the range was 240 meters. So basically, again, see that symmetry applies. If this point of time and this point of time are symmetrical here, then this distance from 0 to x1 should be the same as this distance from x2 to r. You know? But because it's like the second part of it is like a mirror image of the first part. So x1 should be the same distance as r minus x2. No? So that's how I'm getting that x1 plus x2 is equal to r. And of course, at this point here, you can see x is r by 2.
Yes, sir. Done.
Okay, people, so hope you have understood this point about the symmetry in general as well as for this particular question. So the final point that we'll understand with the symmetry is something which is anyway very obvious, that the impact speed that the projectile has on the ground when it comes back at capital T time is the same as the projection speed. So at time t equal to capital T, you can see that the velocity is u cos theta I cap plus u sine theta minus gt. Now that t will be basically what? That t is 2u sine theta by g, we had just seen. Okay, so this will be 2u sine theta by g. So not surprisingly, it is just minus of u sine theta. So the impact speed, which we can write with that symbol vi, is u cos theta I cap minus u sine theta j cap. So the impact speed at t equal to capital T is the same as the projection speed, and it's symmetrical in direction also. So if we projected something like this at this angle theta, when it comes back and hits the ground, it hits the ground with the same speed, but with a symmetrical angle. The angle is now below the horizontal. Earlier it was above the horizontal. At same theta with respect to x-axis. But only thing is, at time of projection, it was, in this case, anti-clockwise, and at this time it is clockwise. Yes.
Sir,
Yes.
till now in all the cases, the point of projection and the point of impact have been on the same height. So, but if there are
Horizontal level. Yes.
so if
Yes.
there are
Yes.
different height, then too the same equations will work, or like we'll have to
No, but
take different cases or something.
see, what will happen now, the four equations that we had written for x and y as functions of time and vx and vy, those equations are universal. But the formula for range, time of flight, all that will change, because your landing is not happening on the same horizontal plane. So where it is landing, your y coordinate will not be 0. So we will have to modify the formula that we get for those things, but the fundamental equations will remain the same. You understanding, no? So that is the case. Like we have different cases, like we have projection from a heighted point, just like we had seen vertical motion from a heighted point. Then we can have a situation where you're even projecting from an inclined plane or from a staircase. So all these will become variations of this. But when we generally say projectile motion, the standard case is this one.
Yes, sir. Okay, sir.
Okay, now the final thing, I mean, the final couple of things for the standard case of projectile motion, we will come to projectile motion from a heighted point and all that subsequently also. Okay. The next two things is, one is the graphs, the important graphs, and they will show us the symmetry apart from other things also. So we will separately plot the x component of motion in terms of vx and x as functions of time, and we will separately plot the y component of motion in terms of Vy as a function of time and the y component of displacement as a function of time. That is the y coordinate itself as a function of time. So these are like all very standard things. This is suppose y as a function of time, and this is the Vy as a function of time. And this is x component of velocity as a function of time, and this is x component of displacement as a function of time. Now, this first part is the easiest because along the x-axis we have a uniform motion. So the velocity remains constant for the entire journey. And so the displacement is a linear function of time till it reaches its destination at capital T. When, okay, so x as a function of time is just u cos theta into t, and vx as a function of time is just u cos theta. And then we assume that at capital T it's abruptly stopping. Now we are assuming it's not bouncing or anything like that. So it's like somebody's caught the object there or is just stuck to the ground where it landed. But Vy on the other hand has the same kind of behavior that we had seen for vertical motion. When you project something from the ground, it starts with a positive velocity, in this case u sine theta, but it's decelerating and the velocity is becoming zero at half time. And then as it is descending from half time to the full time, symmetrical. So it comes and hits the ground with a y component of minus u sine theta. So remember Vy was u sine theta minus gt. So that's this graph. Okay. And accordingly, the y component of displacement will become that quadratic parabolic kind of graph. So this is capital T. Because it's that quadratic graph, it has that symmetry that exactly at halfway it reaches the maximum height. So this is our y is u sine theta t minus half gt square. So if you write it in factorized form, you can see how we get this condition that at halfway it's reached the maximum. So these are these four graphs. So these four graphs also show you the symmetry of the ascent and descent. Yeah, I'll scroll up, just give me a moment.
Sir, done.
Yeah, done, no? Okay, now once you understood these graphs, one final thing here is what we call the trajectory. So trajectory is a fancy word for path actually. Trajectory or path of a projectile. That is, what is the exact shape of the curve that it follows. Okay, so that we get from the equations. X as a function of time was u cos theta t, and y was as a function of time was u sin theta t minus half gt square. Now in these two equations, if we do what I'm saying next is that if the variable t is eliminated between equations 1 and 2, what we'll get is we'll get a relation between x and y, okay, which represents every point x comma y in the actual path of the projectile. So that relation is then called the equation of trajectory. Equation of trajectory is basically the equation of a set of points which represents the path. So each point on that path, each coordinate x comma y, it satisfies the equation of that path, which we get by eliminating time between these two equations. So how we eliminate time between these two equations? So from equation 1, we take the value of t as x upon u cos theta, and we substitute this in equation 2. So we now get this relation that y is equal to u sin theta into time, which is x upon u cos theta, minus half gt square. So that is this. So you can see now that we are getting a relation between x and y. So that relation represents such a curve that all points on that curve are satisfied by that path, or all points on the curve satisfy this equation. So they represent the actual points that that particle has gone through during the projectile motion. So you notice here that this is a quadratic relation. So I'll come to that. This is called the equation of trajectory for a parabola, sorry, for a projectile. So if we were to plot this curve on the xy plane, it would represent the actual path, because every point on this curve is satisfying equation 1 and 2 at some point of time or the other. So if we were to plot all the points one after the other, the projectile is going through, those points would be represented by this equation that we have written over here, by this curve of the equation. That is why it is called the equation of trajectory.
Yes, sir.
So
Yes.
it should be x tan theta minus half g.
Yeah, sorry, my mistake. It's x. It's a minus sign here. Please make a correction, all of you. There's a minus sign here. Okay, so the final thing is what you notice here, that this is actually a parabolic curve because tan theta is a constant. It's not a variable. And this term, so let's say it is alpha, suppose. Okay. And half g upon u square cos square theta. This is also a constant. It's not a variable. So let's say it's beta. So y is equal to like alpha x minus beta x square, where alpha and beta are some constants. So you can see that it is a quadratic relation, which means that the path is parabolic. It is a parabola in shape. That's why we say that projectiles have a parabolic trajectory. So this actual path in the xy plane on which the projectile moves is the shape of a quadratic curve or a parabola. So as a projectile moves from its starting point to the point where it lands, in between this point is where it is at r by 2 comma h and all that. So any point on this curve, it satisfies the relation y is equal to is some constant into x minus some constant into x square. Yeah, theta is basically the angle of projection. So that is the angle at which we have thrown it at t equal to 0. So it is not something which is changing with time. Now, understood the point? Both u and theta are to do with at the instant of projection. So they're not changing with time. So this is the parabolic trajectory or the path as the shape of a parabola, which is given by this equation. Okay, so we will see that this final thing, which is called the equation of trajectory, this is also useful in solving certain type of problems. Certain types of problems where we are more interested in the geometry of the path rather than on time dependent equations. The examples we have solved today were more to do with time, that at time 2 seconds, what was the velocity, what was the displacement, things like that. But we will see in more advanced level questions, often we are solving things which are required with respect to geometry rather than, with respect to time. So the geometry of the path, whenever we are solving something related to that, the convenient way of solving will be making use of the equation of trajectory, which is this one. Whereas anything which is time based, when we solve, we will use the fundamental 4 equations that we discussed earlier. That is x and y as function of time and vx and vy, those things. So those are the kinematics parameters as functions of time. So those things will be used whenever we are solving anything time based. Whereas this equation of trajectory will be used whenever we want to solve something geometry based. So we will learn how to use these in different problems. Okay. But anyhow, so this completes the theory part of projectile motion. Next lecture, we'll pick up some more questions, and also I will keep aside some doubts solving time from especially the worksheet number 1. I will send worksheet number 1 again on the group, especially for those who have shifted to the Blue House group from other groups. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Bye, sir.
Can you go up a minute?
Yeah, sure. This part? Yes.
So, sir, the graph.
Achha, the graphs. No?
Sir,
Yes.
Sir, just wanted to ask one thing that in the case of free fall,
Hmm.
sir, in the case of free fall, we had three equations.
Yeah.
Sir,
V is
one
equal
of
to GT, है ना?
yes,
Y
sir,
is
that
equal to S is equal to half GT square. That those
yes,
equation,
yes, yes,
yes.
yes. So, sir, in that, there you had written V is equal to GT, so it would be U is equal to GT now.
नहीं बेटा, U is initial velocity, na? And V is always what we write at a time t. So you can see if you substitute t as 0 in that equation, your U comes out to be 0, na? Because we had dropped the object. In free fall case, we are dropping it, na? So we are not projecting it with some initial velocity.
So, sir, what would be V is equal to GT?
Yeah, V is equal to GT, na? Because your initial velocity, see, your initial velocity was 0 because you dropped it, and your acceleration was G. You know? So V as a function of time is what? U plus AT. So substitute now. So it is 0 plus GT. So at any time t, what is the velocity? It is G into T.
Can you scroll down a bit? The last graph.
But sir,
Yeah.
then in that case, very next example you had given to find the impact speed. So, sir, can you tell what is the impact speed, the initial velocity or the final one?
No. Impact speed is the speed with which it hits the ground below. So you drop the object from a height h above, no?
So impact
And
speed
then
is nothing but the V, right?
it's the velocity at a specific time when it hits the ground.
So what is that VI? VI.
Impact speed, no? It's impacting at the ground. Okay.
Sir,
So
can we
see,
write as V final? Means final
you
velocity.
can write it as anything. You can write it as V prime, V final, you know, V impact, whatever. But see, this is at some general time, and this is at specifically the time when it impacts the ground. So that time is capital T, no? So capital T, remember, was how much? Square root of 2h by g.
Yeah, sir. 2h by.
Impact speed is becoming how much? It is becoming g into capital T, no? So that's how it became square root 2gh. Or you can use the third equation also for that.
Thank you, sir.
Yeah, sir. Yeah, sir. Got it. Sir. Got it. Actually, there was a confusion in writing, sir. Thank you, sir.
Okay. So impact speed is the specific speed at that time when it's hitting the ground. Whereas when we write V as GT, it is the instantaneous speed. It's not specific. No? It is at any time t in between. Got my point? That's the difference between the two.
Yeah, sir. Yeah, sir. Got it.
Sir, can you go to the question that you gave today?
Thank you,
The
sir. Bye,
question,
sir.
okay, bye. Question I gave, which one? The numerical problem?
Thank you, sir.
Yes, yes, sir.
Yeah, that was here. This one, no?
Yes, sir.
Okay.
Sir, here the last one, the third one, velocity average. Sir, how is the answer 40? I can.
See, you have to divide the displacement by the time. No? So displacement you just written in the first part, it's 80 meters along the x-axis. And what is the time between 2 and 4 seconds? It's 2 seconds, no?
Yes, sir, but if we do that V4 minus V2 means velocity at 4 seconds minus velocity at 2 seconds.
So that is for average acceleration, beta. Delta V by delta T is average acceleration. But here we are calculating average velocity, na? So that is displacement upon time. So it will not
Yes,
come
sir,
from
got
V2.
it. Yes, sir, got it. Thank you.
Okay.
Sir, in cases of projectile motion, we like the only force we usually use is gravity, or like suppose we can take a
Yeah.
case of buoyant
In
force.
our understanding of projectile motion, there's only gravity. If there's any other force, then we will not call it projectile motion. We will call it a different variation of motion.
So like suppose like it's a similar case, but like suppose if you throw something that is less dense than water into water with a certain velocity, then like it will also
That's
follow
a
the
different
same.
case. So then the buoyant force will play a significant role. So we cannot use these equations.
Yeah, sir. So just the acceleration instead of gravity will be the buoyant force, right? It will be caused by the buoyant
No,
force.
but then there'll be both the things, gravity and buoyant force, both will be active. So we'll have to calculate net force is equal to mass into acceleration and then use that acceleration in the equations.
Oh, okay, sir.
You understand? So net force will become buoyant force minus weight because buoyant force is upwards and weight is downwards.
Yes, sir.
Got it? No? So if the object is more dense than water, then net force will still be downwards. If the object is less dense, like a wooden block or something, then the net force will in fact be upwards.
Yes, sir. Thank you, sir. Bye, sir.